So in the H-2 experiment, what we're doing is we're looking at a nanoparticle haloing system where we're looking at a bimodal particle size distribution and a bimodal particle charge distribution, which will help stabilize the entire system. We're trying to determine what is the exact nature of the stabilization mechanism and then how we can utilize that to actually create crystal structures in 3 dimensions. One of the key issues that we run into when we perform these experiments on the ground is that gravity forces the crystallization to happen on a 2-dimensional surface, which means that we only can get one type of crystal structure. And we know that that crystal structure is based only on the large particles. It does not incorporate the small particles. By doing these experiments in microgravity, we're hoping to be able to drive the crystallization of both the large and small particles simultaneously so that we can incorporate both particles into the ultimate structure. One of the key aspects of this work is to determine exactly what is the mechanism of nanoparticle haloing, as that is one of the biggest questions that exists in literature currently. Additionally, it allows us to actually move more from a theoretical perspective into the applied aspect of the work where we can actually start utilizing nanoparticle haloing for direct application. One of the primary applications is in the development of quantum dot-based solar cells, where you're going to use the small particles to generate a charge when it's hit by a photon of light, and you're going to use the large particle as your charge carrier to drive charge to the electrodes. Another area is in the development of photonic crystals, specifically for switching in the telecommunications industry, where you sometimes need to go from an optical signal to an electrical signal, back to an optical signal. We can get rid of that center point and just do a complete optical signal all the way through the switching process.